Hi there. Today we're going to look at Mastering Atari Games with Limited Data by Weizhou Ye, Xiaohua Liu, Tanahard Kurutach, Pietra Biel, and Yang Gao. This paper presents the EfficientZero model, which is a model that can do reinforcement learning with severely limited data. So the paper tackles the Atari 100K benchmark, which means to learn the Atari benchmark, as a reinforcement learning task, as for example DeepQ networks did, but you only get 100K transitions. It's about 2 days worth of real-time data to work with, and after that the model supposedly be able to play Atari. So this is a variant on MuZero, which is an insanely data-intensive reinforcement learning algorithm, and it introduces various tricks and various amendments to MuZero to make it more sample efficient. So when we look at this paper, you can see the gist of it right here. If you do this Atari 100K benchmark, you can see that a lot of the other reinforcement learning algorithm, they fail to even reach human level performance, whereas this new algorithm outcompetes not only the other RL algorithms in this low data regime, but also the humans. Here they say, EfficientZero's performance is close to DQN's performance at 200 million frames, while we consume 500 times less data. EfficientZero's low sample complexity and high performance can bring RL closer to real-world applicability. They even say we implement our algorithm in an easy-to-understand manner, and it is available at this GitHub address. So this code is out there, especially if you want to do reinforcement learning, but you don't have as much compute or time or money. This might be for you. So we'll go through the paper. We'll see what the improvements are. There's not a single improvement. There are many improvements, 3 big ones to be exact. And yeah, if you like content like this, don't hesitate to subscribe and tell your friends and family and professors, I guess. All right, so we'll first take a small look at what MuZero does, just as a recap. I have done a video on MuZero, but if you haven't seen that, then here is a very short introduction to MuZero, to the algorithm. So in a classic reinforcement learning setting, you have your basic setup of, you have the environment and you have the actor, and the environment gives the actor some sort of an observation at time step, let's call it t. The actor uses that observation to come up with some sort of an action at time step t, and then the environment gives the actor back a reward for that time step and the next observation, t plus 1. And that goes on and on and on. So the question is, how is the actor supposed to come up with this action right here, given the past observations that it has seen from the environment, in order to maximize all of the reward that it gets? Now, in a regular reinforcement learning algorithm, let's say in the simpler reinforcement learning algorithm, what people are doing is they're doing model-free reinforcement learning, which essentially means that they take the series of observation 1, observation 2, and so on that they've seen so far. They take that, they stick it in a big neural network, and they train it to output some sort of an action. And they train the neural network in order to maximize this reward right here, usually using some sort of policy gradient or something like this. So this is a rather direct way. We call that model-free reinforcement learning, because you directly predict the action without an explicit model of the world. Now, when you have a model of the world, so when this environment here is well described, for example, a chessboard. In a chessboard, you know the rules. You know everything that's going to happen in a chessboard. You can use a model of the chessboard. So what you can do is you can take these observations, and these observations would correspond to some defined state, or let's say tic-tac-toe. Tic-tac-toe is a better example. So, with the observation, I can actually construct the board of tic-tac-toe that I'm in. And then what I can do is I can actually search. So I can try out. I can say, okay, what if I put something here? Oh, then my opponent's certainly going to do that right here. And then what if I put something here? And then my opponent's going to do that, and then they win, right? So that is one way to do it, and usually you visualize this as a tree. So you are here at a root node, that's your state, and you have several options to do things, and in these several options your opponent has several options, or if it's a one-player game you have several options again, and so on. So what you want to do is you want to search this tree for the best possible path. And this is what things like AlphaGo, AlphaZero, and so on did. They have this explicit model, and they search through it. And now the neural networks no longer predict actions directly. The neural network help you search through that tree, which means they vote essentially on which paths of the tree to explore, because the tree quickly becomes too large to explore as a whole. Right? You can't, like, if it's more than 3 moves ahead, the possibilities just get giant, even like especially in a game like Go. So the neural networks are here to guide the tree search, and that was, in general, the techniques of that center around the Monte Carlo tree search, because at some point you abort the search and you simply play one game to the end as sort of an approximation of what happens, and so on. I'm not going to go into that super duper right here, but what MuZero does is, MuZero says, well, this whole tree search stuff essentially only works if I have an explicit model of the world, such as the tic-tac-toe board is clearly defined how it works, right? Also, I can have a simulator for it. I can rewind. I can try again. This doesn't happen when you're interacting with any sort of real world thing, let's say, or even the Atari benchmark. So in Atari, I know there's hacks where you can save the ROM and so on, but essentially you're not supposed to go back in time or go forward in time. You're not supposed to be able to try something out and then say, well, no, that didn't work. I'm going to search for a different path in the tree instead. So what people do is they try to learn a model of the environment. So in absence of the model of the environment, they try to learn one. And there are many, many different ways of doing this. And what MuZero does is it learns a latent model of the environment. So how does that look? So here you have the current observation T. What MuZero does is it uses a neural network, I think they call this H or something, to get this into a hidden state. So they map the current observation into a hidden state, and then they plan using the hidden state. So they say, okay, I'm not going to predict what the next observation is going to be, like in the tic-tac-toe board. I'm only going to predict what is the next hidden state going to be. T plus 1, like this is 1, this is 2, this is 3. So, depending on which action I do, what is going to be the next hidden state of the environment. Of the environment. What's going to be the next hidden state? And from that hidden state, I'm always going to predict what's going to be the reward for transitioning there. What's going to be my own policy, which is a bit weird that you have to do this, but you have to. And what's going to be sort of the value. And the value is what is going to be my future reward when I go from here. So these are the sort of things that MuZero predicts, and with that, it is able to search this latent tree. Note the addition to to AlphaZero, which is this run right here. So we might label this. This is something like reinforce. This is AlphaZero, and this is MuZero. So the difference to AlphaZero being that we no longer have an explicit model. So in order to do tree search, we have to learn a model, and the model that MuZero learns is in the latent space purely, right? It doesn't predict future observations, and it only learns all of this from the signal that it predicts the reward, it predicts its own policy, and it predicts the future value. And those are the only learning signals for the world model. That is good because it focuses the algorithm on what's essential. It is essential to get the maximum reward possible. And therefore, the more the learning signals center around those concepts, the better. But that also means learning an entire world model just from signals like the reward is extremely sparse. So it uses a lot of data. And that's essentially the catch right here. So we're not going to go into how exactly MuZero does Monte Carlo tree search. They have a way of balancing exploration and exploitation right here by essentially using an upper confidence bound formula that you can see right here. So EfficientZero goes and says there are 3 main weaknesses with MuZero. First of all, they say lack of supervision on the environment model. That's what I just said. All the latent model of the environment is learned purely from the signals of the end, from the reward signal, the value signal. These are single numbers. And to ask the model to learn a transition function for the environment model is a big ask, and of course needs a lot of data just from that. The second one is hardness to deal with aleatoric uncertainty. I've given up on trying to remember which one is aleatoric and which one is, what's the other one? Epistemic? I have no idea. Okay, let's just read the paragraph. The predicted rewards have large prediction errors. So if there is uncertainty in the environment, for example, the environment is hard to model, the reward prediction errors will accumulate when expanding the Monte Carlo tree search tree to a large depth, resulting in suboptimal performance in exploration and evaluation. So what they mean is that if this reward right here has a bit of an error, and then I go on searching, right, these branches right here, and then the reward I predict right here also has a bit of an error, and so on, and we go down the tree, and every reward has a bit of an error. What I'll do in order to, at the end right here, I have a path, and I don't go to the end. I stop after a while, and I add up the rewards that led me here, and that's sort of how valuable this node is, plus the value that I predict right here. That's going to be the value of this path is going to be the sum of the rewards until I'm here, plus the value from here on out. And if all of these little rewards have little errors on them, that quickly adds up to a big error. So that's their second criticism right here. That's something we're going to have to solve. And thirdly, off-policy issues with multi-step value. And that is a general thing in these reinforcement learning algorithms. The more distributed you make them, the more sort of what people usually do is they have like a learner box in the middle, learn. So there's a neural network there, but then they have a lot of actor machines. So they distribute training and interacting with the environment, and these send back data. There's usually a replay buffer right here somewhere. And that means just that the neural network that is here at the learner is not the same that generated the data, because the data is kind of old. And until you use the data to practice, the neural network will have already learned from other data, and therefore you get an off-policy issue, even though it's an on-policy algorithm. Now, MuZero does a little bit to correct this, but they say this has to be done more. So how are they now we tackle these 3 things. So the first thing they tackle is this lack of supervision on the environment model. So what they do is they add a self-supervised consistency loss. You remember that we map the observation at time t to a state, a hidden state at time t. And then we use our latent model to predict for a given action what's the state going to be at time t plus 1. And that's an estimate, right? Now, what this paper says is that, wait a minute, if we simply look at what happens in the real world, right? observation t plus 1, and we send it through the same, so through this same encoding function, then that gives us the hidden state at time t plus 1. So technically, these two things here should be equal. So the hidden state at time t plus 1 and the estimated hidden state at time t plus 1, they should be kind of the same. So what they do is they use a self-supervised consistency loss that they nap from SimSiam. So SimSiam is a contrastive learning framework or self-supervised learning framework, and it's usually used to have two images which have been differently augmented, so to make their representation equal. So the model learns to sort of ignore the data augmentation. That's how you train self-supervised image models. But here we don't augment differently. What we do is we take an observation and we take the observation at time t plus 1. And the first observation, we actually map it through that function that is supposed to give us this estimation of the next state. And then we use a similarity loss in order to pull those two things together. So this function that gives us the next state and the representation functions, they're now going to be trained in order to make those two things, the next hidden state and the estimation of the next hidden state, similar to each other. In fact, the left branch right here is the one that's trained, but that includes the representation function and the next state function. So you might ask, this is kind of the first question that everyone in MuZero has, is like, why is this not done? Because this is, if you look at the loss of MuZero, you can pretty easily see that that is possible. And I think the MuZero authors have deliberately not introduced a loss like this because they say, no, if we learn from just the reward signals, that is going to be a better algorithm, even though it might use more data, but at the end, it really trains for what is important, for what is the end goal, and that's why they didn't introduce a loss like this. Introducing a loss like this clearly trades off what the actual target is, namely optimizing the reward, right? We actually don't care if anything's consistent. We simply want a higher reward. So it trades that off for sample efficiency, because now the supervision signal here is much, much larger, because now we work with different hidden states, which are entire vectors. So that's going to be a much better signal. So that's the first improvement. The second improvement is what they say, end-to-end prediction of the value prefix. So they make an example right here of saying, okay, what's the value? If you look at this, you have to predict sort of the future value. Can you really predict what's it going to be? Like either the green player, let's say the ball flies in this direction, the green player is going to catch the ball or not, right? And that makes a huge difference. Now, you as a human at this point, you know that the green player is not going to catch that ball. And at this time, you're kind of sure. But it's quite hard to predict at this time right here. And it's even harder to predict when, at which step in time that player is going to miss the ball. And that's an argument they make for essentially saying, if we add up the rewards of our own predictions, they can introduce a lot of mistakes. But that's exactly what we do. If we look at the Q value that we use in this tree search, what we do is we add up the rewards that we got in the path so far, and we add the value at that particular path. And that is very error prone because this sum right here accumulates all the little errors that happen in prediction. And as I said, if we're not exactly sure at which point, that is just one of the examples to show you how hard this problem is of predicting rewards step by step if you look into the future. So what they do is pretty simple. They say instead of adding up all the rewards, k steps into the future, what if we simply take the hidden states that we predict k steps into the future and just shove them into a neural network. And then that neural network will output the sum of the rewards. So instead of summing the rewards directly, we have a neural network output the total sum, much like we have a neural network that outputs the value function that looks ahead. This neural network right here, it will look sort of back. It will look into the past from the current state to the end state that we rolled out in imagination. It'll predict the entire value. They use an LSTM for that because it can take in arbitrary number of states. And the LSTM has per step rich supervision because we have a reward at each step. And therefore, they say that works quite well. So that's the second thing. The third thing is the model-based off-policy correction. So, this one is a little bit more tricky, but essentially, we can see, where is it? Okay. We can read a bit through it to see what it does. This is an off-policy correction mechanism, and they have two different mechanisms to do off-policy correction. I already said off-policy correction, you have to do it because the data that you get to learn from comes from your replay buffer, comes from delay from the network and so on, and is a little bit older than the network that you're learning. And that turns out to be quite a big problem. So, what we usually do is we sample a trajectory from the replay buffer and we compute this target value z right here for the value function. The value target suffers from off-policy issues since the trajectory is rolled out using an older policy, and thus the value target is no longer accurate. Now, MuZero reanalyze, this is a particular version of MuZero, already handles that a little bit in that it actually recomputes the values, the scalar values, with the current network before it learns from them. But still, the policy used to generate that data is from an old policy. And so they say, when data is limited, we have to reuse the data sampled from a much older policy, thus exaggerating the inaccurate value target issue. So what they do is they say, well, instead of using sort of the path, so this is the state, right? And here is what actually happened, right? We took some actions. That's what actually happened. And now what we would like to do is we would like to take this and learn from it. Right? But the policy used to generate that path is an old policy. So the current network might have done something entirely different. It might have done a different action right here and got to a different point. And that is a problem because in an own policy method, we'd largely like to learn from actions that have been generated with the current policy. So what they say is that we're simply going to not use the entire trajectory for learning, but we're going to cut off at some point because, of course, the further out, the more uncertain we get. And that cutoff point is going to be closer the older the trajectory is. So for a very recent trajectory, we might cut off towards the end, but for a very old trajectory, we might cut off like all the way here. And then what we do after the cutoff point is, so we take this, we cut it off at some point, we say, well, it's old, but this part right here is still sort of, the uncertainty is not large enough for us to worry so much. And then what they do is they use, because they have a latent model for the world, they use that model to imagine a rollout. So much like something like Dreamer or so, they now train using imaginary rollouts from the point where they cut off. So the trajectories in the replay buffer are more like seed values. And after that, they imagine rollouts using their latent model of the world. All right, so I think that's it. We redo an MCTS search with the current policy on the last state and compute the empirical mean value at the root. Oh yeah, so at the last node right here, they redo an MCTS search. They in order to get a really good target value there with the current policy. Yep, that's it. Okay, so these are the 3 improvements. Again, they introduce a consistency loss on the hidden states to make their transition model better. Second, they directly predict the value, what they call value prefix, this thing right here, instead of summing up the rewards as they go along the tree search. And thirdly, they use the collected trajectories as seed values and then train essentially in half-imagined rollouts with the current policy. So that's it. So what does that give them? It gives them very good performance on this Atari 100K benchmark. They do some additional things right here, additional ablation studies. For example, they try to reconstruct the observation from the hidden state, and they see that, for example, if you don't have a consistency loss, this quickly fails. So this would be the original MuZero, whereas with the consistency loss, you can see that kind of, sort of, there is something right there that looks like the observation. Now here, I don't know if that is after the 100K steps, because of course MuZero after 100K steps also doesn't perform super duper well, and therefore you wouldn't be surprised like that this is, or it could be because their reconstruction method is just kind of poor as well. But the difference is noticeable between the 2 models, the one that has the consistency loss and the one that doesn't. They also analyze, for example, the validation loss if you directly predict the rewards, or if you use this value prefix prediction method. You can see during training it's approximately the same. However, at validation time, this loss is much, much lower. And lastly, well, they do a lot of ablations. That is it. What I was surprised, or not surprised, what I noticed in the ablations, and this is pretty much in all the ablations, there is no consistent ranking. So they have 3 improvements right here. And sometimes this improvement right here, for example, will be the most valuable. So you can see that without the value prefix, alien drops quite a bit. And in other times, you can see right here, this one will be the most valuable. And yet in other times, some other one, like the last one, will be the most valuable. Don't see one right now, but I have looked at it, and there is no consistent thing. So that it means that there's not a single recipe to make this thing better. It's a conglomeration, and for different Atari games, different things are important. And that sort of leads you to think, is this isn't the method from, let's say, principle. This is, they have looked at what fails, and they have fixed essentially one by one the major mistakes that they found. And that is a way to go about it, but it is also a danger that we sort of over-engineer to the benchmarks that we have, because clearly if I just put one of these improvements, then some of the Atari games will improve by a lot, but others won't. And that, to me, is a little bit of the danger right here. And this is why I'm not, I can't tell you if this algorithm is going to be a staple algorithm for sample efficient RL, or if it just works particularly well on this benchmark. They do another benchmark. They do the DeepMind control benchmark, but I think there's going to be more evaluation needed. But yeah, I'm excited. It really has the potential to be something cool. All right, that was it from me. Thank you so much for listening, watching. Let me know what you think in the comments, and bye-bye.